Welcome to exercise 1.3. Today we're gonna calculate basic parameters of an oscillation, and you already saw these parameters in lecture of week 1. Just quick reminder. First of all, you have learned that the amplitude of a function is the maximum or the minimum value of that function, and the amplitude is defined as x roof. And now we're going to switch to Matlab and calculate exactly that amplitude from our results of the simulation. Here you see again the script from the previous two exercises. We defined all the parameters and we calculated the differential equation, and the results are the displacement and the velocity. And now we want to calculate the amplitude of that displacement. And therefore we define a new section which is called calculate amplitude. And within this section we're going to calculate our amplitude, and the amplitude is just the maximum of the absolute value of x of t, and we call that x roof. And actually that's it already. Now we can run the script and we see that our x roof is 0.0265, and we could also just quickly plot our results with the plot functions within Matlab. And you can see, if we compare that to our plot, that we already derived our amplitude. We have calculated our amplitude, and now the second part is to calculate our time period. Our time period is a time between two maximums. And in order to do that, we switch to Matlab again, and we define a new section which is called calculate time period. And in order to calculate our time period, we actually need to find the peaks of our oscillation, and Matlab provides a function which is called find peaks, and you can find, as the function says, the peaks of that. And the function returns a vector with local maxima, just maxima of x of t. And we're gonna save that in the variables maxima and max location. Now you can see that I also put in the variable time. The variable time is our time vector of the simulation, and I put that in because now the find peaks function can give us the maximum locations time-wise. So if we run the script, we can see that the function found 3 maxima and also gives us the time locations of these maxima. And of course, we want to have the time period, so we just have to subtract these time locations. And we're gonna do that by a function called diff, which gives us the differences of adjacent elements. So let's run the script, and you can see that we now have a time period vector with 2 identical values. So our time period is 0.77. So we calculated the time period. The next one is to calculate the eigenfrequency and the angular eigenfrequency. As you already know from the lecture, the eigenfrequency f0 and the angular eigenfrequency omega 0 are dependent on the time period. And since we already calculated the time period, we also have these 2 values. So we actually just need to use Matlab as an ordinary calculator. In order to do so, we define a new section which is called calculate frequency and calculate angular eigenfrequency. First of all, we want to calculate our frequency, which is just 1 divided by the time period. In order to do so, we have to choose only the first element of the time period vector, but since both should be the same, it doesn't actually matter, and you can also use all other values of the time period vector in order to check if your calculation is correct, because they should be all the same. And then we calculate the angular eigenfrequency by multiplying the frequency with 2 and with pi. And Matlab provides the constant pi within its code, so we don't actually have to look up what number pi is. Now we can run the script, and we have the frequency, which is 1.2987 Hertz, and the angular eigenfrequency of 8.16. So we calculated the eigenfrequency and angular eigenfrequency, and now we want to calculate the phase angle. The phase angle is the angle which defines the starting point of the displacement function. And you can see here in this oscillation that actually if you have a usual cosine function without any phase angle, you would start at this point. And the difference between this point and the 0 point, time-wise, is the time t phi. We have to calculate this time t phi in order to calculate our actual phase angle. And how we can do that is we can plot our velocity x dot, and you can see that the velocity x dot is 0 at this point. And if you put that constraint into your equation, then you can set x dot to 0, which is 0, and you could put in for t the time t phi. And of course, you know that x roof and omega 0 can't be 0, because then we wouldn't have any oscillation. So the sinus function has to be 0. And if the sinus function have to be 0, the argument of the sinus function has to be 0. And then you end up with equation like this. And if you rearrange this equation, you end up with the equation for the phase angle phi. And you can see that you can now calculate the phase angle phi by omega 0, which you already calculated, and by t phi, which we now calculate with Matlab. In order to calculate the phase angle, first of all, we define again another section, which is called calculate phase angle. And now we want to find the 0 crossing points of the velocity. And in order to do that, we first of all have to find the signs of the velocity function. So for a positive velocity, we want to have positive sign, and for negative velocity, we want to have negative sign. And we can do that within Matlab with the sine function. And then, if we just take the differences of adjacent elements, you can get the 0 crossing points. I'm going to show you now how to do that. First of all, we need a temp variable. Now we have a look at this temp variable. So you can see the temp variable is always 0, since we have the same sign of the velocity for these points. And here you can see that it's a non-zero value, and that means both elements have to have another sign. And there you can see that there is some zero crossing going on. And in order to find these points in the temp variable, you can use the function find, which will give you the indices of non-zero elements of a vector. So now we defined a variable index up, which gives us the zero crossing points from negative to positive, because all the values in the temp variable which are greater than 0, they give us the points where the velocity goes from the negative to the positive. And the other way around, you get the points where the velocity goes from positive to negative. And these indexes I'm going to store in the variable index down. And of course, we don't want to have only the indexes, but we want to have the exact time where you have that crossing. And therefore, we can just define a variable which gives us the corresponding time to the indices. Now index uptime and index downtime should give us all the times where we have a zero crossing. And of course we want to get the first zero crossing point, and therefore we have to find the minimum of these two values. And for that case we can use the minimum function of Matlab. Now we have actually all we need. We have the angular eigenfrequency and we have the time phi, which is first zero crossing variable, and therefore we can now calculate the phase angle in radians. And if you also want to have the phase angles in degree, you can convert phase angle radians in degree by using the factor 180 degree divided by pi. And now we can run the script. And we can also, in order to compare our results, we can plot our actual velocity plot. And here you can see that at this point we have a zero crossing, and you can see that one also here in the index down at the position 15. And you can see that we have a phase angle of 65 degree. And if we plot now the displacement, you can see it here that this distance from the maximum here to 0 point corresponds to 65 degrees. And this is the end of this exercise. Now you have learned how to calculate all the parameters of an oscillation.